coming to the fourth appointment of this year. We were counting how many people we had already up to now, and it's still even more international. Now we managed to switch continent even, not just country. So today we have Kramer from Brazil, but doing his PhD at the University of Modena and Reggio Emilia here in Italy. And today he's talking about scheduling Meteheuristics, right?
Yes.
Yes, you didn't change the title.
It is
And so, welcome.
So, good afternoon. Thank you everyone for coming. And so I'll try to explain a little bit this work that was my master thesis in Brazil. So, and this work was me and Alan Subramanian, that was my advisor. So these works we made when I was in Brazil, and as Alberto said, now I'm doing my PhD here in Reggio Emilia. What is the outline of the presentation? So I will show firstly introduction, so talk about the problem, so the definition, the problem definition, a little bit about the motivation in the literature. So I will not talk too much about the literature because as in the title of the presentation, it's a class of scheduling problems, so it's a bit difficult to talk about the literature, about like 20 problems. And then I'll show the methods, so the Metaheuristics, and talk a little bit about the neighborhoods, and focus the presentation in a small part of the move evaluation. So then I'll show some experiments and conclude the presentation. So the class of Earliness and Tardiness scheduling problem, or class of just-in-time scheduling problems. So the name is because in the just-in-time, when I schedule a set of jobs on the machines, I have to penalize if a job finished before its due date and after its due date. So maybe it's more common to penalize the jobs that finish after the due dates, but in the just-in-time, if I finish before, I also have to pay something. And in this class, the problems are usually NP-hard. And here we have some features, some characteristics of the problem. So multiple machines, setup times, and release dates. So here is a formula to try to define the problem. So this definition is for the more general problem that we are solving. So if I have this problem and I start to change, for example, release dates are not considered, for example, I have another problem. If I don't have setup times, another problem, and so on. So in the scheduling problems, I have a set of jobs that should be scheduled in a set of unrelated parallel machines, and I have this data. So for each job in each machine, I have a processing time of a job. So if I have a set of unrelated parallel machines, the processing times of a job J will change in the different machines. So for each job I have a due date, I can have also a release date, and I have the weights to pay for the earliness and for the tardiness, and I can also have a setup time, so machine and sequence dependent setup times. So if I will process job J after job I in machine K, I have to do the setup time. So the main objective is to schedule all the jobs in the machines. In this problem also we don't consider preemption, so I can't start to process a job, stop its processing in the middle of the job and then processing after. So it's not allowed. So the release date and the setup times and the more general problem that we are considering, they are present. And another problem when I have earliness, for example, is to insert idle time. So in some solutions, for example, for some instances, may be better to have a machine that they are not processing any jobs because to avoid the earliness, for example. So the objective is to minimize the total weighted earliness and tardiness. So in classification that was proposed in the scheduling field, I can represent this problem with this notation. So I have to minimize the sum of earliness and tardiness subject to release dates and with setup times in a set of unrelated parallel machines. So this is the definition for the more general case. So if I, for example, if I, instead of a set of unrelated parallel machines, I have a set of identical parallel machines, and without release date and without setup times, so I will have another problem. So with this problem and these particular features, I can have all these problems. So this is the class of problems that we work with. So the motivation is the problems are usually NP-hard. In that table that I showed before, there are some problems that we can solve in polynomial time, but these problems are not in the table, so we are not considering these problems. So these problems, particularly scheduling problems, are faced by the companies, so are real-life problems. And also, when we saw in the literature, the number of papers, the number of works, considering idle times is not as big as the number of papers, the number of works to the problems that don't consider idle times. So when we can insert idle times in the sequence, we have now also to solve the timing problem. So, for example, in the Metaheuristics, for example, when I have a new solution, so for all new sequence, I have to solve the timing problem. That is, I have to say when all the jobs will start. So I have the sequence, and if I have a sequence, I'm interested in have the optimal sequence. So I have to solve the timing problem. So in the literature, in our works, we found more than 120 papers in the last 25 years. And there are exact approach, meta-heuristics, and there are also a lot of papers focusing on efficient local search that we also considered in our work. So let's talk about the method. So it's based on iterated local search. In our case, we are considering multi-start iterated local search. And why these meta-heuristics? We found in a lot of problems, for example, in routing problems, with these meta-heuristics, it's possible to obtain high-quality solutions. And the components of this Metaheuristic are basically the procedure to generate initial solutions, the local search phase, and the perturbation. So, this is the idea of the method. So, it's not possible to see. Sorry for that. But the idea is in our method, because we know, for example, if idle time is allowed, so I will try to solve, for example, the timing problem. So if I have a problem without idle time, so I will the idea is to choose different methods during the moving evaluation in the local search. So the idea is basically to generate initial solution. So here I will check if the problems considers idle times and setup times. So it depends on the problem. I will choose different method for the move evaluation. So then I will do the perturbation, and here basically the acceptance criteria. So here it's like a zoom in the move evaluation. So if I have a problem without idle time and without setup times, I can use a move evaluation based in this work. So usually, if in the move evaluation or the evaluation of neighborhood, I have to perform all cube steps. But in this paper, in this work, they show that's possible to do it, to evaluate all the neighborhoods in n squared. So, if I don't have idle times, but I have setup time, so I can use another kind of move evaluation. And if I have idle time and Earliness start is another one, and idle times without Earliness and Tardiness, without Earliness, I can use the straightforward move evaluation. Because, for example, if I have release dates in my problem, but without Earliness, I also have to solve the time problems. But in this case, the time problems becomes trivial. So, why I will use this method if this method is easier? So note that this method, this move evaluation, with this move evaluation, I can solve all the problems. But computational times are really important. So to the initial solution, we implemented two procedures. So the first one is all random. So I will choose a job at random and put in a machine at random. And the other one is based on the earliest due date, average dates, based on the grasp constructing phase. So when we perform the experiments, we also saw that the initial solution don't helps a lot during the local search, or doesn't help too much with the convergence. The local search is performed by the randomized variable neighborhood search descent. So the idea is I have a list of the neighborhoods, then I select one of these neighborhoods in the list at random, and if these neighborhoods improve the best current solution, so I will fill the list again, and I will stop the local search only when the list becomes empty. So if I have 5 neighborhoods, and the first one, the second one, the third one, the fourth one didn't find a solution that's better than the current solution, but the last one it's possible to improve the solution, so all the neighborhoods goes back to the list and the procedure will keep going. The perturbation we'll solve after that is basically some movements that we consider during the local search, but in this case I don't want a solution that is best than the current solution. So I will perform one of these movements at random. So I choose, for example, 2 blocks at random, and I will swap these 2 blocks to perform the perturbation. And the neighborhoods that we implemented in our methods are based the inter-machine and the inter-machines neighborhoods. So I have parallel machines, so I have the neighborhoods inside this one machine, in between 2 machines. So it's basically the L block insertion. So the idea is to get a block of size L and move in the sequence. L prime block swap, so swap 2 blocks of size L and L prime. Here inside the same machine, and here between 2 machines. Here is just how we represent solutions. So we can use this block representation. So it's better to show how the neighborhoods works, and also to explain the move evaluation phase. So here is the L block insertion into machine. So here I have my current sequence. Then I get a block of size L. Then L is a parameter of the algorithm. So if I have 2, 3, or 4, so I have 3 different neighborhoods. So the idea is to get a block and insert in another position in the same sequence. So forward or back. The L prime block swap inter-machine. The idea is to get 2 blocks. The first one with size L, the second one with size L prime, and interchange the position inside the same machine. And the same neighborhoods are inter-machine. So the idea of L block insertion to get a block from one machine and put insert in another one. And the block swap is to get a block of the first machine and change and swap with a block in the second machine. So it's like 4 neighborhoods structured, but if I put the parameters, if I use L 2, 3, and 4 for L block insertion, so now I have already 3 different neighborhoods for the L block insertion. So the size of the blocks are a parameter of the method. So before we run the experiments, we perform the parameter tuning also to choose the best size of the blocks. And the size of each neighborhood is n squared. So for each neighborhood, I have n squared moves that can be performed. And the straightforward move evaluation for each movement can be performed in n. So the overall complexity for evaluating neighborhoods is n3. And for problems that I have to solve the time problem, so this complexity go up. So here is almost the same thing that you saw in the box. So if I have a problem without idle time, I can use the straightforward move evaluation with an overall complexity of n3. But if I have a problem without idle time and without setup time, I can use this method, this idea, to evaluate each movement in constant time. If we don't have idle time, but we have setup times, we can use this method that was based on the method from Earliness. I can also evaluate a movement in a constant time, but because of processing phase or pre-processing steps, the overall complexity is bigger than in this case. But it's also better than the straightforward case. And when we have idle time, we have to solve the time problem that can be solved by dynamic programming, for example. And the overall complexity goes up again. But if we use the method proposed by Ibaraki et al., it's possible to reduce this complexity. Here, I will focus on this case, because in my master thesis, we get the same idea of the authors, and we generalize it for the case with parallel machines and for our neighborhoods. So, we only propose this method for the problem to minimize the weighted tardiness on a single machine. For these three neighborhood structures. So I'll extend it to the unrelated parallel machine case and to our neighborhood, so to block neighborhoods involving blocks. And the idea of this method is to compute the cost of each block and sum up the cost of these blocks to obtain the cost during the neighborhoods evaluation. So here, if I have this function, so wjk, that will give me cost of a block starting for the first job in a given sequence until the job j. So, for example, here the cost of the block 1, if here is I minus 1, so will be given by w I minus 1. Okay, so I have to pre-process this function for each sequence before perform the neighborhoods. Here is another function, so rho jkt will indicate the penalty if I start to process in job j on machine k at time t. So here is also I have to compute it at the beginning of the algorithm. So I will compute it just one time. It's like I have the data will be translated in this function. So if job j starts at time t, so I will have a penalty. So in this function, these functions are non-negative, convex, and piecewise linear functions. So I will have some breakpoints on this function. So in the case without release date, this function will have two segments. So basically, the due date will define when the function will change the slope of the function. Here is another function. It's most the same idea of the function wj. So in this function, I will have the cost of a block starting at job j or at position j until the end of the block. So the idea is to use this function to have, for example, the cost of a block start at position j on machine k, start at time t. So with this function, I will compute the cost of a block. So here is just a small example to show how to obtain the function g. So the function g I obtain using the function rho. So the idea is basically to sum up the many rho functions. So each rho function refers to a job. So for example, if I have this sequence and I have the function g for this block, so I have to sum up the whole function for the job 1 and from the job 2. So if I sum up rho 1 and rho 1 and rho 2, I will get the function g. And note that the breakpoints are a fundamental idea of this method, because I'll try to explain later. So here is just how we store the functions in the memory. And here is the idea how to compute, how to get the cost of a block. So I have to work on the breakpoints. So, for example, if I want the cost of the block G1 for machine 1, start at time 5, for example. So if I start by time 0, I have to arrive to the window in which time 5 is in, and then compute the cost. Here is another important data structure. So it's the processing list. So it's also pre-computed for each sequence before each neighborhood. The idea is to get the processing time of the blocks. So if I will perform the neighborhood L block insertion, for example, and if the block is size 3, so here I will have a list with all the blocks with consecutive jobs, 3 with all the blocks with 3 consecutive jobs. So the idea is to get the processing times of these blocks. So we have these auxiliary data and auxiliary functions. So WJK, so for each sequence before neighborhoods, I represent the cost of a block starting with the first job in the sequence until the job J. Whole J KT that I will use basically to create the functions G that represent the cost of a block starting at the job J, or position J, until the last job in the sequence. And here the processing list that we use to access the function G in a specific order. So the processing list and this function is the two structures that allow us to perform the move evaluation in constant time. Yeah, so the idea in the straightforward move evaluation, so I have for each movement, for each sequence, I have to recalculate the cost of all the jobs in the sequence, so it will be n steps. And in this case, if I have the function g, so for example, I want to know the cost of a block start at position 2, on machine 1 at time 5, for example. So I go on the function G, and I will walk on the breakpoints, and I will find the window, and I will have the cost. So if I have the same function for the same block of jobs, but starting now in another time, so I have to go from the beginning again, into the beginning again. So if I do like this, it will be the same thing as the straightforward move evaluation. But the idea is yes, the idea is, for example, here in the swap neighborhood. So if I swap these two blocks, and if I don't have idle time, no setup times, so what can I see? So for example, the first block, the cost will be exactly the same. So I can get the cost of this block with this structure, so it's a constant time. The last block is also the same thing, because this block will start exactly at the same time, so I can get the cost with this structure. In our implementation, the blocks that we are swapping are usually small, so at most 4, not more than 4, the size of a block. So we decide to calculate the cost of this block in a straightforward way. So is that because we don't have any square. And the problem here is to have the cost of the block in the middle of the sequence, because this block will start at different times. And I will use the functions G to get the cost of these blocks. But if you have, take a look here in this function, for example, if I have an I that is fixed, for example, I and J refer to the position of the blocks that I'm exchanging. So I is the beginning of the first block, and J is the beginning of the second block. For example, if I fixed, I have an I fixed, then the time here depends only on the parameter G. So this expression is exactly what we have in the processing list. So here, for example, I will have a list of times. If I change J, so I have like n different times. And using the processing list, I can access these times, in this case, in an increasing way. So here, for example, I have to evaluate this function for all these times, but now I will just walk in through the breakpoints. I will just walk one time. I will not start from zero and start from zero every time. Because, for example, I know that the first time, according to the processing list, will be smaller than the second one, and the third one will be smaller, will be greater. Sorry. The last one, so I just have to walk in forward on the breakpoint. So that's the point that makes possible to reduce the complexity. It's not easy to explain. And now I'll show a bit about the results. We coded in C++ on this machine, and running Linux. So in the first table that you saw at the beginning of the presentation, we saw like 40 problems, I guess. But another problem is that it's not possible to find publicly available instance for all these problems. So we run our method only these problems with results and instances available. And also in some cases with a single machine, we also didn't run our method, because the methods of Tanaka is like something from another world. It's not so. Yeah, it's an exact method that performs too much better than the heuristic, so it doesn't make sense to perform. But we performed the experiments. We find the optimal solution, but we didn't report it because. So we run our method basically on these problems, always with multiple machines. Here with identical parallel machines, and here with related parallel machines. And in the last case, we have idle times. In this case, the results that we found in the literature, even if we have earliness phenons, but the experiments by the authors, they didn't consider idle times in this case. So here, we run the method without idle times. Here is a bit about the parameters. So here, with these parameters, we can define the neighborhood structure that we use. For example, here we can see how many block swaps we implemented. So here we saw that the ILS that we implemented are also a multi-start version, so the number of restart is set to 10. Here is a parameter for the ILS, so it's the number of consecutive perturbations without improvement. So for problems with idle time, we reduce because of computational time, because of the timing problems. Here the first problem is a parallel machine, identical parallel machine to minimize the total tardiness. So we have this instance, but a small instance of 20 or 25 jobs on at most 10 identical parallel machines. So we run our heuristics 10 times for each instance, and in at least 9 of 10 runs we find the optimal of the instance. So for this set of instances are instances with 20 or 25 jobs are small instances. For this case, it's identical parallel machines again. Now to minimize the weighted tardiness. In the case that we saw before, the weights are always 1 for all the jobs. And here we have instances with 40, 50, and 100 jobs on 2, 4, or 10 machines. So 25 instances for each combination of jobs, number of jobs, and number of machines. And for the instance with 40 and 50 machines, jobs, we found all the best node solutions. And the average time is also better than the authors. And here for the instance with 100 jobs, this method, in this paper, they implemented exact method. So sometimes they have available optimal solutions, and sometimes they have only upper bound. So for this instance, we can also improve some best node solutions. And here the authors, they didn't report the time, the average time. Here is the same problem now with penots for Earliness also. Note that that in this case idle time are not considered. And the author proposed more than one metaheuristic method. And here also, if you saw the results, we improved some best node solutions, and we found also the best node solution. If you saw about the time, we can say that our time, our computational time is more. So for the case to minimize weighted tardiness or unrelated parallel machines, so unrelated parallel machine, the processing time of the jobs are different on the machines. And in this set of instances, for each group, we have 60 problems, 60 instances. And the methods also from these authors, they provide some optimal solutions. And when the optimal solution not found, they provide open bounds. So we compared these results. For this case, we found all the best node solution, all the available optimal solution, and we also improved some open bounds. So if we compare our average time, the average time of the authors is almost the same, but in some case we have a time that's better, but in the other case the time is a bit worse. And here for this problem, now with idle times and to minimize earliness and tardiness, we compared the same authors, and we found all the optimal node solutions, and also we improved some open bounds. So our results was capable to find almost all the best node solutions. And the average time is also, for some group of instances, are similar, but for the instance a bit bigger, our method becomes a bit time consuming. So to conclude here, so we propose an algorithm for a class of problems, but our algorithm is able to solve a large amount of problems, but we consider some particularities. So about the release dates, the idle times, and the setup times, for example. So what I showed here is a bit about generalization of the Earliness method, about the local search, efficient move evaluation, and the results are also good results, like this. So we submitted the paper, is now on second revision, and you can find more details about the other move evaluation schemes, for example, and these technical reports. And as future work, what we expect to do is to generate or to create a new instance for some problems that we don't have publicly available instance, and develop exact method to solve this problem, to provide initial lower bounds or optimal solutions, and with the heuristics, for example, also to provide some open bounds, some initial results. So thank you for coming. If you have some questions, thanks.
Is there any question? I have one, but in these problems that you consider, there never is any hard constraint on, for example, earliness or tardiness?
No, in the last problem, we considered the here. Yes, we did without release date or setup times.
Yeah, but I mean, you always have a penalty,
Yeah.
but there is never a hard constraint, right? So you, in the worst case, you get very, very penalized. But
Yes.
when you do a move in your neighborhood, it never happens that the new solution is infeasible.
Yes.
Right? Okay.
Yes, but our method, for example, we can consider the deadlines.
Mm-hmm.
So if I have a release date and deadline, so it's like hard constraint.
Okay.
But we didn't find also in the literature problem with this configuration.
So this cannot help because every time you do a swap or whatever, you don't have to check if
Yeah,
the
yes,
solution is
yeah,
feasible or
yeah,
not.
yeah.
You just need to evaluate how much
Yes,
it costs. And
Yes.
I see. Okay. That was my only doubt. Anyone else? Then thanks again.